Since the first railways were rolled out, they have explored new frontiers, conquering nature at its most extreme. No matter what lies in their path, inspired engineers endeavour to find a way through. But there's one geographical challenge that stands above the rest: mountains. Overcoming the planet's highest peaks requires phenomenal railways. But they face a unique set of problems.
Behind me we've got the Lithgow Valley, and in front of me we've got Sydney. And these mountains basically act as a great divide between city and country.
The geological conditions are really difficult here. The danger that rocks are falling down is high.
This area has very deep fjords and very steep mountainsides, so it's really difficult to build anything here.
Travelling through mountains is a huge challenge for both track and train. History's locomotives have achieved great things. From the pioneering days of steam to the efficiency of electric and the mighty modern-day diesels. All have made their own mark, but have one thing in common. They struggle on anything steep. It takes a very special railway to climb mountains. On the wild west coast of Britain lies the spectacular Snowdonia National Park, for centuries a mecca for climbers. At the centre of it all, the summit everyone wants to ascend. Mount Snowdon. But at over 1,000 metres tall, these stunning views were once reserved only for the brave. At the end of the 19th century, however, one man decided he wasn't content with merely hiking to the top. He wanted to conquer the tallest mountain in Wales by train. Snowdon Mountain Railway has been clawing its way through the clouds for more than 120 years.
Engineer 1, Snowdon 1.
Mike, pass the message, mate.
Yeah, just to confirm, I believe number 5 is going out first.
This morning, they're preparing the historic rolling stock for another remarkable attempt on the summit. It's been an all-night process.
It's always a busy time prepping for the day. So steam locomotives, they've been in steam overnight with a fireman on watch.
Some of the locomotives are over 120 years old, and they're facing a seemingly impossible near 8-kilometre climb.
The terrain is difficult. The steepest gradient on the mountain is 1 in 5.5. For every 5.5 metres, the track rises a metre. So it's quite steep.
This daring adventure is the brainchild of one man. Railway tycoon Richard Moon had a vision of bringing the mountain to the masses. Today, fireman Elizabeth Partridge, driver Robert Henry Jones, and general manager Alan Kendall are all following in Moon's footsteps as they and a carriage full of adventurous tourists attempt the journey to the top.
Okay, ladies and gentlemen, can I have tickets, please?
But it's far from certain they'll make it all the way.
We are on wind warnings today. If wind speed increases on the mountain, we may be forced to stop at Rocky Valley, okay?
There'd always been an interest in getting to the top of the mountain for 300 years, really, and prior to the railway, people walked and hiked and climbed and also went up by donkey and horse.
Moon's proposed route started from the base of the mountain, passing a sheltered rocky outcrop to traverse a 1 kilometre long exposed ridge, before ascending the last 200 metres to the summit. But no traditional railway could ever provide enough traction to scale the steep incline. A fact clear to current senior engineering manager Mike Roberts-Shaw, down below in the yard.
Well, in a normal railway, all the traction and braking forces is carried out by the steel wheel on the steel rail. In our case, because the gradients are so steep, you get no adhesion between the steel wheel and the steel rail, and the locomotive would just sit and spin or slide backwards.
Mobile 5 to Snowdon 1, stopped at Hebron.
The consequences of slipping back down such a gradient are unthinkable. But there was a possible solution, one that had been perfected by a Swiss engineer just a few years before.
The absolute only option to go to the summit was a rack and pinion railway.
Unlike a traditional train where the power is transferred down an axle to the wheels, Moon's Snowdon locomotives have a cog on the axle, which connects with a toothed rack running between the rails, meaning getting enough grip is no longer a problem.
Well, this is a rack and pinion railway. This part is the rack, and these are the pinions. And on the main track, there's a pair of racks, and on the locomotive, there's 2 driven axles, each with a pair of pinions. So the pinion, there's always 2 teeth fully engaged in the rack.
It was a brilliantly simple solution to a once impossible problem. But whilst the system can cope with the gradient, the unforgiving mountain climate is another matter.
The weather on Snowdon is always a challenge all the year round, and particularly in the winter. We are in July. You can see the cloud coming in. You can feel the temperature drop.
Mobile 5 to Snowdon 1, do we have an idea on the current wind readings?
Snowdon 1, Mobile 5, yeah, the last wind reading at 45 was 45.1.
If the weather deteriorates today, the train will be forced to terminate some distance below the legendary summit. Cloud and mist have shrouded the peak just as they did on the railway's opening on the 6th of April, 1896. After successfully reaching the summit, locomotive number 1 started its descent, but having lost control, jumped off the rack. The crew leapt clear, but the runaway engine derailed and fell over the side of the mountain. Some way below, a climbing group told of looking up, only to see a steam locomotive falling out of the cloud. After an inquiry, additional gripper rails fixed around the track's rack would lock the trains firmly in place. Today, it's an anxious wait for crew and passengers, while control decides if the weather is too severe to continue to the peak.
Paul, you may proceed to the summit on 09, mate.
Mobile 5 to Snowdon 1, proceeding up to the summit on 09.
It's good news. But first, the train must navigate the steepest part of the track.
The upper mountain is a serious gradient, 1 in 5. We're currently travelling on an original locomotive from 1896. You can look out of the window and you can see the gradient behind you. You can appreciate just how hard that boiler has to work and the pressures that it has to create.
The steep gradient means an ordinary boiler would be unable to cope. A traditional steam engine boiler consists of a cylinder filled with water surrounding a series of pipes. All very good for travelling on a flat line. But if you're trying to climb a mountain, as the train tilts, the changing water level exposes the pipes, with potentially calamitous consequences. So how can the danger be averted?
So this is one of our locomotives that we're doing some work on. And this part here is the boiler. And as you can see, it's inclined forward at an angle. And that's so that when the locomotive goes on the mountain and the chassis goes upwards at the front, the boiler becomes level.
It's yet another brilliant solution that means Richard Moon's mountain dream can be accomplished.
Mobile 5 to Snowdon 1 and the summit past the 1 in 5.
As once again, this astonishing train achieves its mission.
Okay, ladies and gentlemen, welcome to the summit. Be very careful, there are high winds today. Mind the gap as you come off and enjoy your stay. Thank you very much.
So here we are, it's the end of July, unbelievably. We're at the summit of Snowdon. You get a real sense of why the original engineering team wanted to build a mountain railway to the top of the tallest mountain. It was not only a challenge, it was something they'd go down in history for. So, hats off to the Victorians.
On a clear day from this station at the rooftop of Wales, it's possible to see England, Scotland and Ireland. Richard Moon's 19th century vision created the journey of a lifetime. Mountain tracks. Railways traversing the peaks and troughs of the world's great ranges. Solving extreme problems in extraordinary environments.
You can see the cloud coming in. You can feel the temperature drop.
But sometimes, for trains, the answer can appear out of reach. Going uphill is all about grip. People are really good at it. Rubber-tired cars are pretty good at it. But with their enormous weight overriding their grip, trains are bottom of the class. This would pose a problem in Australia's Blue Mountains. A 3,500-kilometre long range on the country's east coast. In the 19th century, this natural wonder was a huge stumbling block for an essential rail line between Sydney and the resource-rich Lithgow Valley to its west.
The terrain in these mountains really poses a massive challenge to railway engineers. Trains are beasts which like to stay on flat, level ground. This terrain really turns that paradigm on its head. The sharp vertical drops in vertical elevation, they're all things that railways really don't like.
Tunnelling was financially unviable. There was no choice but to build a mountain railway like no other. The Great Zigzag. Completed in 1869, this remarkable Z-shaped track clinging to the mountainside is in an engineering league of its own for rail enthusiast and driver Lee Wiggins.
The Zigzag Railway deserves to be celebrated and known for its structural integrity and history, and the fact that it is still in existence and still going strong and still as strong as the day that it was built.
It was engineer John Whitton who believed the railway could take on the Blue Mountains. His smart Z-shaped design meant he was able to reduce the gradient to a manageable 1 in 42, meaning the trains had enough friction to ascend and descend safely.
Trains have a lot of problem working on grades that are too steep. You might not be able to start the train on a grade, you might not be able to stop the train on a grade if it's too steep. You're not able to carry as much freight, you're not able to carry as much load.
The shapes solved one issue, but Whitton also had a problem with getting trains to negotiate the track's acute corners. He achieved this by creating 2 reversing points.
Here we are at Top Point's reversing station. Normally steam locomotives would have come powering up the hill here, a locomotive at both the front and the rear of the train. As soon as the train would park up around the corner, the locomotive at the rear of the train would then take control, the points would be switched, and the train would come steaming off towards Sydney up in the other direction.
Whilst the railway may have been simple in theory, executing it in the Blue Mountains proved to be anything but.
When they were first surveying the route for the zigzag, the surveyors themselves were actually lowered off the cliff edge in wicker baskets down the side of the cliff face. After it was surveyed and the line was then designed, it was nothing but manual labour.
Such a colossal project required a huge workforce across the vast area. Luckily, the site offered a natural observation point.
So this seat here was cut into the rock by the engineers at the time that was constructing the railway, and it allowed them a great vantage point over construction. They could see right across the valley and see all different facets to be able to allow construction to take place.
In all, 85,000 tonnes of rock would have to be removed to cut the ledges for the track.
Where we're standing right now is a ledge. This ledge is where the rails run, and this was carved by hand. This was done by hammering drills into the rock and then blowing the cliff apart with gunpowder. Here we are, about 20 metres down from the top rock ledge, and we can see evidence here of the drill hole going all the way down to the base where the charge would have been loaded here at the bottom.
The work was so arduous that it took 700 men 3 years to complete the railway. Today, this group of volunteers is getting a taste of just how tough it was to create the drill holes for the explosives.
As you can see, what back-breaking work this must have been. Doing this for just 15 minutes really goes to show just how hard it was back in those days. No hydraulics, no mechanics, no engines, just good old-fashioned hard work.
Finally opened in 1869, the new cross-mountain route between Sydney and the Lithgow Valley proved an emphatic success.
The zigzag opening in the 1860s certainly benefited Sydney greatly and really opened the mining industry and the agricultural industry of the plainlands this side of the Blue Mountains. One of the first steel blast furnaces in New South Wales, if not Australia, was in Lithgow. So it really opened up the industrial, let's call it, revolution for Lithgow and the central west area, and the zigzag was critical in achieving that.
Today, a network of tunnels cut through the mountains, and the zigzag is operated as a tourist attraction. Nonetheless, it remains an outstanding milestone for mountain rail lines.
To come up with something that drops as far as this does, to be built by hand by people hanging from baskets 700 feet above the ground, I think that needs to be recognised as a major engineering masterpiece of the 19th century.
Safely negotiating acute gradients is an incredible achievement. But this isn't an option for all mountain railways. When climbing steep slopes, something has to give. And often it's speed. So, when a mountain railway covers vast areas connecting cities and towns, and speed is of the essence, somehow its trains need to find a way to travel on the flat. Graubünden in southeast Switzerland. A region world-renowned for one thing. With such a mountainous terrain, you'd think cutting a railway through this dramatic landscape virtually impossible. But for well over a century, this centre of tourism and business has been connected by something truly mind-blowing. The Rhaetian Railway. An almost 400-kilometre network built to overcome nature at its most extreme.
The biggest challenge is the height. 30% of our railway net is 1,500 meters over sea level. So the climb, the weather, mountains, these are the big challenges.
It It was Dutchman Willem Jan Holtzboer who pioneered the railway's first line in 1888. The 50-kilometre stretch from Landquart to the spa town of Davos would spell the start of a railway phenomenon that now boasts 10 lines threaded through the region. And one of its most dramatic and demanding is the Albula line.
It's definitely not the easiest place to have a railway. I wouldn't say we are the toughest, but we are one of the toughest railway engineers here.
It's up to engineer Gilbert Zimmerman to keep the railways running.
The biggest challenge is the height. 30% of our railway net, it's above 1,500 meters over sea level.
Mainline trains are only capable of dealing with up to 7% gradients, so keeping the track as level as possible here means going through the mountains. With the original Albula tunnel over a century old, the team must build a new one through around 6,000 meters of complex rock.
We are going now into the tunnel, the Albula Tunnel 2, the new one. We started building this tunnel 2 years ago, and now we are in the geological fault zone, the most difficult part of the whole project.
The fault zone is full of water channels, creating problems for the team.
With all this water and soft rock, there's a big chance that it breaks down everything. So please don't go any further than here, because this is dangerous.
In these unstable conditions, blasting is out of the question. The team can only dig, and before this can start, the rock has to be strengthened.
We put cement into the rock with high pressure to stabilize the whole thing, to make it more harder.
Once firmed up, only up to 1 meter a day can be dug, despite mammoth machinery.
T-Rex is coming. Now we're going to see how it opens the rock.
To date, this painstaking process has managed to create as much as half a kilometre of tunnel. Not all of the excavation, however, is quite so labour-intensive. The team tackle this colossal project from 3 points. To the north and centre, soft rock requires digging, but to the south, harder rock allows a more dynamic approach.
This is the granite. It's a real hard rock, a dream of every miner, because it's stable, you can blast it easily.
And with today's blast, the miners have to clear a further 4 meters of tunnel.
We are drilling about 120 holes to blast. These holes we fill up with explosives, about 500 kilos. Every explosion, every blasting is exciting.
A blast this big requires a series of carefully orchestrated explosions, which can last up to 12 seconds.
This piece of cord connects the blasting master with the explosive material at the tunnel face. With this, he starts the explosion process.
With the tunnel clear,
We have right now the permission to blast. We are ready.
it's time for action.
3, 2, 1, go! Viva! I do this not every day, so my heart was beating a little bit faster.
As the dust settles, today's progress is revealed.
I'm really pleased right now. A clear face. The rocks are not too big. It's a regular hill of these rocks.
Once the blasting is completed, the new Albula tunnel will ensure high-speed trains can continue to travel on the flat.
A satisfying moment right now, just perfect.
high-altitude railways, pushing engineers to their limits as they tackle nature's most demanding terrain.
The Zigzag is a major engineering masterpiece.
And one fleet of trains faces more problems than most. The Rhaetian Railway. One of Europe's greatest mountain networks, cutting through the heart of the Swiss Alps.
So you have been lucky. This is the Glacier Express, and now you smell food because they are cooking now for the guests on the Glacier Express. Yeah, that's true.
Whether tunneling beneath or crossing above, building a railway through these great peaks requires daring engineering solutions. Perhaps none more so than the town of Brusio, an alpine stop on the Bernina Line. Today, geotechnical engineer Kurdin Kantieni is making an inspection.
Here we're in the Poscavo Valley, a very steep valley that was shaped by glaciers during the last ice age, and those cliffs are still steeper than they actually should be geotechnically. That's what still causes rockfall.
With these unstable conditions, rockfall directly onto the rail track is a constant threat.
On the 14th of December 2008, about 40,000 cubic meters of loose rock material came off. You can actually see the spot up there where it broke off and covered the whole railroad track.
This catastrophic fall closed the rail line for several months. A solution was needed. On the mountain side of the track, an 8-meter trench has been dug to catch any rockfall.
If the dam wasn't there, especially the big boulders would be able to come down all the way into the valley bottom, eventually hit a house.
This engineered defense proved its worth in 2013, withstanding another significant landslide. Today, things are looking good.
So here we can see the railway. On the right-hand side, we have the slope with the old rockfall deposits. There are a couple of fresh stones, nothing big, so I'd consider it a normal situation.
The rock defense system is a brilliant solution to keep the rail line safe, but it's not the only railway structure that it protects. Brusio sits high above the valley floor on a steep slope, too steep for any train to negotiate.
To overcome that steep gradient, they could have built tunnels, but they already thought about tourism 100 years ago, and they wanted people to have the sights of the valley. So they really had to think about ways to make the railway go wide, so it doesn't have to go that steep over the cliffs here in the valley.
With space severely limited, getting any trains up or down from an elevated station seemed out of the question. Until engineers came up with an inspired innovation. The Brusio Circular Viaduct.
The Brusio Viaduct consists of 9 pillars. The train starts there, and it goes all along the loop, follows the viaduct, and then it is 20 meters higher in the very same spot, which is unusual for a railway, and then more or less flat into the Brusio train station.
With its 70-meter radius, this brilliantly engineered geometric shape and resulting gentle gradient ensures trains have an easy ride.
The problem might have been challenging, but the solution that they found was very easy. It's only a railroad track going in a loop, and to me it looks very beautiful. It is a very beautiful bridge, and it will probably outlast every one of us.
But elsewhere in the world, there are high-altitude ranges so hostile, they fill even the most daring engineers with trepidation. Picture battling rocky terrain and near vertical slopes for years on end. That's what it takes to complete a mountain railway. But before you celebrate, consider running it when winter descends. This can be a very different story. California's Sierra Nevada mountains, facing up to 20 meters of snow each year. It would seem like the last place on Earth to build a railway. However, in the late 19th century, the pioneers of California's Central Pacific Railroad thought otherwise. The railway was built to connect San Francisco to Utah via the Sierra Nevadas. By 1869, the section to Reno was almost complete. But there was still one major hurdle to overcome, as engineer Chris Potts is finding out.
This is Donner Pass, and this summit stood as the last major obstacle for the Central Pacific Railroad for joining California with the East.
Named after George Donner, the leader of a settler group, this 2,000-meter-high pass has an ominous history. During the winter of 1846, the travelling party became trapped by deep snow. After supplies ran out, to survive, they resorted to cannibalism. 24 years later, despite the evidence of impassable snowfall, the pioneering rail engineers pressed on.
Theodore D. Judah, the chief engineer for Central Pacific, thought that the weather up here would be no match for his railroad. Unfortunately, he severely underestimated the power of nature. Shortly after the completion of their railroad in 1870, many miles were lost under the snow, and it was deemed impassable.
Traditional snowplows relied on the momentum of the train and a wedge-shaped nose, which works a treat until the snow deepens and turns to ice. With no machinery to tackle deep drifts, Judah built 40 miles of snow sheds to protect the track. But these smoke-filled tunnels were a temporary fix. Finally, in 1883, Canadian inventor Orange Jull provided a solution with a groundbreaking machine. The rotary snowplow. A truly monumental snow battling solution.
This absolute monster of engineering is the last word in snow clearance. If there's a serious snowdrift, this is what the railroad rolls out. Amazing.
Today, the conditions may be fair, but riding this iconic machine is a once-in-a-lifetime opportunity.
This machine runs off of 1,500 horsepower, operated by that B unit right behind us. This plow can clear massive amounts of snow in minutes. What a feat of engineering. Absolutely amazing.
Unlike those traditional wedge-nosed snowplows, Jull's machine relied on an entirely different mechanism.
This fan works like a giant corkscrew. It cuts away at the ice bit by bit, and what it does is it turns the snow into a fine powder, and then through the centrifugal force, shoots it out through the top in either direction.
With Jull's 12-foot fan able to tackle even the worst build-up, it would revolutionize snow clearance.
So not only could this snowplow move more snow than traditional methods, it was also much safer. Not needing the momentum that more traditional methods needed, this was able to operate for longer distances and at lower speeds, meaning there was less of a chance that this would derail. Shortly after its introduction, the rotary snowplow proved itself time and time again in the most severe weather conditions.
In the winter of 1952, Smart Ridge near Donner Pass experienced a huge blizzard. The city of San Francisco streamliner was buried in around 5 meters of snow, trapping over 200 passengers. Although it took 3 days, no less than 4 rotary ploughs finally reached the train, saving all but 2 of those on board.
Since its introduction in 1870, the rotary snowplow has fought the worst weather and won. It truly is the ultimate snow clearing machine.
Mountain railways, overcoming mighty peaks, allowing millions to enjoy some of the planet's most mind-blowing scenery.
They wanted people to have the views of the valley. To me, it looks very beautiful.
But some railways aren't just for seeing the sights. FlRm, a remote Norwegian community. Situated at the southern tip of the country's longest fjord, during the early 1900s, this isolated town was all but cut off from civilization. Connecting to the Bergen Railway 20 kilometers away would change their fortunes. But with the main line perched nearly 900 meters above, achieving this would be far from easy. As geologist Trine Helle-Simenez knows.
Here you can see clearly why it was so difficult to build a railway. You have really steep and very tall mountain sides with lots of fractures. And in the bottom of this steep valley you also have the river. So to build a railway, it actually had to hug the mountainside and wind its way upwards the valley.
Only an extraordinary feat of engineering would overcome nature this tough. The FlRm Railway. One of Europe's steepest standard gauge train lines. Clawing its way up to the main line, crucially connecting FlRm to the outside world. A journey that never fails to impress CEO Sivert Bach.
I would like to welcome you on board the FlRm Railway.
The FlRm Railway starts at 2 meters above sea level, and it goes through a typical Norwegian valley from the Ice Age up to Myrdal station at 867 meters above sea level. It's considered one of the steepest railways in the world.
In 1923, it was senior engineer Ferdinand Björk who was tasked with making the FlRm Railway a reality. The 20-kilometer line from Sognefjord to Myrdal station in the mountains would pose enormous challenges.
You have these steep mountain sides. You have rock falls, avalanches when building. The climate in the upper parts is really Arctic. It's a really big challenge to do this thing.
Add to that waterfalls and treacherous ledges. To bypass as many obstacles as possible, Björk commissioned no fewer than 20 tunnels. Around 200 tunnellers were brought in to cut through the mountainside in grueling conditions.
My great-grandfather, he was building railway tunnels in the mountains. He always liked to tell stories and about how they lived. And the heaviest thing was to drill up in the roof of the tunnels. They had to do everything like up like this. It was very heavy work. I think it took like 1 month to drill just 1 meter of tunnel.
Today, with the train line complete, geologist Trine continues the family's railway tradition above ground, tackling a potential problem that could bring the mountain rail line to a grinding halt.
When you have such steep cliffs, it's obvious that you will have rock falls. There are lots of fractures, the mountains are very tall, so rocks always fall down. It's very easy that the railroad could be hit by rocks. So you can see actually how loose these rocks are. So these small things fall down and can happen also to big ones.
And today, the team have spotted something that could spell danger.
What I've seen here is that there's a block with fractures on all sides. It's quite huge and heavy. You can see the train is just passing us down there. If one block like this falls down, it's dangerous for the railway and for the people, and we want them to be totally safe.
Rock fractures like this are often caused by a phenomenon known as frost wedging. This is where cycles of freezing and thawing water trapped inside the rock can cause it to break away.
So, this is the block I think you should put 3 bolts in.
Combating this requires an ingenious solution.
This could be looser, but this is bigger. Don't you agree?
A traditional method dating to the 1800s, known as rock bolting.
Evel is now down checking how many bolts we shall have and that we agree and how the blocks look from down there. He's going to drill 3-meter and 4-meter long bolts into the rocks to fasten them to the solid rock. And then when you have the hole, you put in this glue. First it has to be mixed in there with the drill, and then you wait for a while, and then everything is glued. This is basically the technique that's always been done, that you fasten the rocks to the mountain.
With several kilometers of open track lying below, this preventative work is vital.
How's it going, guys? Everything okay?
Yeah.
Good. This work is really important because, you know, if any rails or anything is damaged, or even this overhead lines, you cannot take the train, so it's really important for the whole area.
The extreme scenery this railway once set out to conquer is now part and parcel of its success.
FlRm Railway has in the last 30 years transformed from a railway who took people from FlRm and made us go to Oslo or Bergen with the railway. And now it's more a tourist railway, and it's increased to about 1 million passengers this year.
All transported to the track's mountainous summit of Myrdal in a journey time once thought impossible.
Well, this morning it took us 50 minutes to get to Myrdal, and in the old days it would have taken a day or two to get from FlRm up to the mountains.
All down to generations of pioneering railway engineers.
Can you imagine more than 100 years ago that somebody stood here looking over the valley saying, like, we're going to build a railway here? That's impressive. This is one of the most remarkable railways anywhere in the world. And I'm able to take part of that. That's fantastic. I'm so proud of it.
Since the invention of the train, mountains have posed railways some of their toughest challenges. Sparking inspired solutions.
This plow can clear massive amounts of snow in minutes. What an incredible machine!
Taking engineering to new heights.
The people who decided to build it were taking a huge leap forward and a huge leap of faith.
Mountain railways all around the world really deserve to be celebrated.
To create impossible railways.
Throughout history, mountain railways have been an important tool for pushing through the boundaries for human exploration.